So the basic formula for angular momentum of a particle about a given point is m r cross v. You can also write this as r cross mv, and mv is nothing but linear momentum of the particle. So angular momentum is r cross linear momentum p. Fine. Where what is r? Let us quickly recollect that if a mass m is moving with a velocity v, okay, and you want to find out its angular momentum about a particular point O, then r is the position vector of the particle with respect to O, with respect to the point about which you want to find out its angular momentum. Okay, so r cross mv, or you can write it as r cross p. Now, when you take position vector cross momentum, we call it as moment of linear momentum. Okay, so you can define angular momentum like this. It is the moment of linear momentum. So r cross p. Whenever you take position vector cross some quantity, we call it as moment of that quantity. Okay, so angular momentum becomes the moment of linear momentum. Fine. So last class we even solved problems based on angular momentum of a particle about a given point. Now let us extend that formula to a system. Angular momentum of a system, and the systems that we consider are rigid bodies for now. So angular momentum of a rigid body about an axis. Okay. Can one of you quickly tell me what are the different types of motion that a rigid body can execute? Or what are the different ways in which a rigid body can move? We had discussed two types of motion that a rigid body can execute. What are they?
Circular motion and translational motion.
Rotational motion and translatory motion. Okay. See, there is a third type of motion also that it can execute. It's called combined translation and rotation. We'll come to that towards the end of this chapter. As of now, for now, we will only stick to translation and rotation. Okay. First, let's say an object is in pure translation. Fine. Can one of you tell me when you say a system is in translation? What is the condition for translation? Fine. If an object is in pure translation, all particles of that object must be moving with equal velocity at a given instant of time. Velocities must be equal, accelerations also must be equal. Okay, that is when we say the system is in translation. See, there is no point studying this chapter if you don't know the types of motion that an object can execute. I mean, if you don't remember, you know, okay, but you should understand that you are learning the concepts of this chapter in order to be able to describe a rotating system, motion of a rotating system. So you should know that we are making that shift, or we are like improving our knowledge of mechanics by considering rotational motion now in this chapter. Till the chapter work energy power, we only consider translation. Okay? The entire object was assumed to move in the same manner. Now in this chapter, we are considering another type of motion called rotation. That is why the name of the chapter itself is System of Particles and Rotational Motion. Okay, anyway, in translation, all particles have the same velocity, including center of mass. So consider one of the particles of this system, let's say m1, assume it is moving with a velocity v1. Okay, or you can say the velocity is v. Every particle will have the same velocity in translation at a given moment. Okay, suppose you want to find out this system's angular momentum. Fine, about a given point. We'll first talk about a point, then we'll go to axis. Let's say there is a point here, O, about which you want to find out the angular momentum. Simple idea. total angular momentum of the system is the angular momentum of the first particle plus the angular momentum of second particle, so on, up to angular momentum of the nth particle. You have to, I mean, it's a vector quantity, so you have to treat it as a vector. Add the angular momentum vectors of all particles of the system, you get its total angular momentum. That's the idea. Okay. Now, with respect to the point O, assume this particle of mass m1 has a position vector r1. Can one of you quickly tell me how much L1 will be? Angular momentum of the first particle about the given reference point. How much will it be, or how will you express it? Quick. Just apply the formula for angular momentum of a particle. It is mr cross v. So in this case, it becomes m1 times r1 vector cross v vector, velocity of that particle. Okay. Similarly, angular momentum of the second particle will be m2 times r2 cross v, and so on. Angular momentum of the nth particle about that point will be mn times rn cross v. Now, imagine adding up all these equations. If you add all of them on the left hand side, you will get L1 plus L2 so on up to Ln. That is nothing but total angular momentum of the system is equal to right hand side. Rishi, tell me which term is common on the right hand side when you add all those terms?
V, sir.
V is common. So how will you express the sum of all those terms? If you want to write it in a single term, how will you write it?
Sigma.
Sigma? Pawan, can you tell? If you add all the terms on the right hand side and express it as a single term, how can you express it?
Sir, V into sigma MR.
Array. If this was an actual class, no, I would have made you stand. That is not into. Tell properly. Anyone? First, one of you tell me the meaning of this symbol.
Cross product of vector.
You are supposed to say cross. Okay, I'm telling this to all of you. Never say into. Now, if you add all the terms on the right hand side and express it as a single term, what would that single term be? Okay, Pawan, what were you about to say? Like, don't say into, say cross and tell what you wanted to tell. Okay, anyone else?
Cross MIR.
Can you repeat? We could not hear everything.
So V cross sigma M1R1.
V cross, okay, M1 R1 plus M2 R2 so on. You want to write it as sigma Mi Ri. Okay, this is wrong. Can anyone tell me why this is wrong, or can any of you tell the correct way to express that sum? Okay, Vanilla, you only tell me. Is there any difference between A cross B and B cross A? Are they same?
No, sir.
Can you change the order of cross product like that?
No.
Now tell your answer properly. You can't write V first and R next. You should never change the order of vectors in a cross product. If you are changing it, you have to add a minus sign. Okay. Now tell properly.
Sigma MI cross V.
It will be sigma MI RI first cross V. Okay. It's very important to keep in mind that the order of cross product should not be changed. If you want to change, you have to add a minus sign. So basically what happens in the first term, if you put V aside, you will be left with M1 R1. Second term, put V aside, you will be left with M2 R2. So add all those M1 R1 plus M2 R2 so on, and then take cross product with V, because every term is being taken cross product with V. Okay, fine. Now, one of you tell me, did we come across this term anywhere? Sigma MI RI.
So position of center.
Good. Tell the formula properly for position of center of mass.
Sigma MI by total mass.
Sigma MI divided by total mass of the system. So sigma MI can be written as total mass of the system multiplied with position of center of mass of the system. Okay. And then that cross product V, cross V will also be there. So that's the angular momentum of a system, rigid body in translation. M RCM cross V. Now what is V? V is the common velocity of all particles of that system. You can also call it as velocity of center of mass. Okay. Velocity of any particle will be same as velocity of center of mass in translation. And see, we have seen this formula before, mr cross v. Mr cross v is nothing but angular momentum of a single particle. But here, which particle is it? Center of mass. So you can say it is the angular momentum of center of mass about the given reference. That's all. So what all this suggests is that you can replace this system, okay, this entire rigid body, which consists infinite particles, infinite number of particles. You can replace this entire system with a single particle placed at its center of mass. Okay, you assume all the mass is present at the center of mass and it's moving with a velocity v. Okay, the common velocity of the entire system. Just find out the angular momentum of center of mass. That will tell you the angular momentum of the entire system. That is what it means. Okay. Now, those of you preparing for NEET, you don't have to bother so much about this derivation. But those of you who are preparing for JEE, okay, mains or advanced, derivations are very important. Okay, because they can twist the definition itself and ask you questions based on it, just to test your understanding of the fundamentals. They want to make sure that you know the fundamentals. Okay, they want to make sure that you know why a translating system's angular momentum is equal to its center of mass's angular momentum. You have to know this derivation. Now, how can they twist the derivation or definition? They can define some other quantity. Okay, like angular momentum is mr cross v, that's fine. They can talk about some other quantity and call it mr cross v dot something, or they can define a new quantity of their own and ask you to calculate that quantity. How will you do? If you only remember the final formula, such questions you won't be able to approach. Okay, so you need to know the fundamentals, how every formula is derived, in which case it is applicable. Everything you need to know if you are preparing for JEE. Okay. Fine. So for a rigid body in translation, angular momentum can be calculated easily by calculating the angular momentum of its center of mass. That is enough. Let's solve problems based on this. Now, just to quickly revise how to calculate angular momentum, the proper formula is m r cross v. Okay, if you know the position vector, velocity vector, you can do the cross product. Otherwise, you can first find out the magnitude, m r multiplied with v perpendicular or m v multiplied with r perpendicular, and then assign a direction, clockwise or anti-clockwise. By seeing, you can tell based on the situation. So let's make use of all this. Assume there's a horizontal surface and a block is moving on it. Cube. Let's assume it's a cube. Where is the center of mass of a cube?
At its geometric center.
At its geometric center. Okay. Not even a cube. Let's assume this is a square plate. Okay. Two-dimensional. For square plate also, the center of mass is at its geometric center itself. Okay. So you know the position of center of mass. And that is important because I'm going to ask you to calculate the angular momentum of this system. So assume this is a square plate of mass some 4 kg and side let it be 5 meters. Okay. And what is happening with the square plate? It is moving to the right with a speed of say 10 meters per second. Okay. Now I'll give you 2 points and you are you need to calculate angular momentum of the square plate about those 2 points. First point we will take is here. Okay. Call this point as A. Where is A? It is at a height of how much is half the side of the square? 2.5 meters. So A is exactly at a height of 2.5 meters above this surface. Find out angular momentum of the square plate with respect to A or about this point A. Next, this point B, which is on the horizontal surface. Calculate its angular momentum about B. Okay. Do this quickly, all of you. I'll give you 3 minutes. Remember that it's a rigid body in pure translation. And for a rigid body in pure translation, if you want to find out angular momentum, you just have to find out angular momentum of its center of mass. So you can imagine it as a single particle and solve. Do it.
Sir, the center of mass of this is the geometrical center.
Yes.
Uh, the angular momentum will be
First, tell me which formula you want to use to derive angular momentum. First, second, or third?
the first one.
You want to use R cross V, M R cross V. Okay. So you
Yes,
have
sir.
to visualize the R vector, V vector, and take their cross product. Now, mass is known 4 kg. Tell me, to use M R cross V, the vector R should be from where to where?
Sir, the vector R should be the A1, the 2.5 meter one.
No. The vector R, if you want to take as it is, from where to where should it be? It's not 2.5. Anyone? If you want to use MR cross V, then R vector should be from where to where? Or what does R mean? We discussed today itself. Okay, anyway. In MR cross V, R is the position vector of the particle with respect to the reference. So in this problem, if you want to use MR cross V, then R vector is supposed to be like this. Position of center of mass with respect to A. Rishi, is this clear?
Yes, sir.
Now you can see its velocity vector, velocity 10 meters per second is to the right. The position vector is also exactly to the right because 2.5 meters is exactly half the side of the square plate. So this height is also 2.5 meters only. Therefore, that position vector is horizontal, velocity vector is horizontal. They're both in the same direction. Rishi, tell me, what is the cross product of two vectors which are in the same direction?
0, sir.
0. M RCM cross VCM. You don't even need to know how long is RCM. That distance is not given to you in the problem. You don't need to know the distance also. The answer is 0. This system has no angular momentum about the point A. That is what it means. And it makes sense also See, visualize its center of mass moving forward. Next instant or a short while later, it will be somewhere here. Then also the position vector will be in the same direction. Sometime later, it will be here. The position vector will be in the same direction. It's not rotating. The direction is not changing. Okay. So that is the meaning when we say, that is what we mean when we say this system has no angular momentum about this reference point. Okay. Hope this is clear to all of you. If you had used any of the other two formulas also, you must have gotten the same answer. Next. Angular momentum about the point B. Aishwarya, can you tell how you're trying to solve? Or how should we solve?
So we can use MVR.
You want to use, okay, you want to find out the magnitude first. M, V, R perpendicular. Okay, good. Now we know the mass is 4 kg. We know the speed 10 meters per second. First tell me, from where to where should R perpendicular be?
Center of point B.
What did you say? Like your voice was breaking. Can you repeat? Center of mass to the point B. Is that what you said? Your voice is breaking. Okay, anyone else? Can you tell me from where to where R perpendicular should be? While calculating angular momentum.
So from the reference point to the line of action of velocity.
Correct. Reference to line of action of velocity of the particle. Okay. Now line of action of velocity of center of mass, you know it's the horizontal line. Okay. Which is at a height of 2.5 meters. So R perpendicular becomes this distance. That is 2.5 meters itself. We don't even know the actual R vector. Actually, how far the center of mass is from B, we don't know. And we need not know also. Okay. So R perpendicular here is 2.5 meters. Substitute that. The answer will be 100 kg meter square per second. Okay. But we have to assign a direction also. Angular momentum is a vector quantity. Pawan, you tell me, as the center of mass moves forward, will it appear to be rotating clockwise or anti-clockwise as seen by B? Will its position vector rotate clockwise or anti-clockwise?
Clockwise.
Clockwise, correct. At the given instant, this is the position vector. We don't know how long it is, but it's in this direction. At a later instant, it'll be like this. At some other instant, it'll be like this. And so on. It's rotating clockwise. And if you curl your right hand fingers clockwise and extend your thumb will be pointing into the screen. So you can write it as minus k cap. Or you can simply put a cross, indicating that it is into the screen or into the plane of the paper. Okay. So if an object undergoes pure translation, this is how you calculate its angular momentum. Just treat the object as a single particle placed at its center of mass and use the particle formula. Is this clear to all of you? Any doubts in this? Okay. Next, if a system is executing pure rotation, okay, means rotation about a fixed axis. In that case, how to calculate its angular momentum? Let's see. Consider a random system. Okay. See, if a system is executing rotational motion, okay, it will have a particular axis of rotation. Right? Let's assume this system is rotating clockwise with an angular velocity omega, and it is rotating about means around. Okay, it is rotating around this axis. Now, why am I putting a cross to indicate an axis? Why not a line? Cross means this line, the axis is perpendicular to your screen. Okay, it is spinning around that axis. That is what it means. Okay. Now also, angular momentum of the system is the sum of angular momentum of individual particles. Okay, this is what you need to take. Fine. Consider one of the particles. Let's call this as M1. Assume it is at a distance R1 from the axis. Okay. Now I'm not talking about point, I'm talking about axis. Okay. Let's say this particle is at a distance R1 from the axis. Fine. Now this system is spinning around this axis. Spinning means, rotating means every particle will be executing circular motion. So M1 will be moving in a circle around this axis. And with what speed will it be moving? Let's call its speed as V1. Can one of you tell me how V and omega are related in circular motion? How are V and omega related?
Omega is equal to V by R, sir.
Okay, omega is V by R, so V is equal to R omega. So we can write the speed of the first particle as R1 omega. Why we write in terms of omega is because since this is a rigid body, every particle rotates at the same rate. Omega will be same for all of them. Speeds may not be same. For example, you take a second particle somewhere here. Assume it's at a distance R2, its mass is M2. Its speed V2 will be R2 omega, different from V1. Okay, so all particles won't have the same speed, won't have the same velocity. Fine. So how do you write angular momentum of the first particle now? Basic formula for angular momentum is mr cross v. Okay, let's take the magnitude. M r v perpendicular or mv r perpendicular. So first particle's mass is m1, distance from the axis is r1, and the velocity it has is already perpendicular to the position vector. Fine. So you can directly write it as v1. I am writing it as r1 omega. So effectively this becomes m1 r1 square into omega. Okay. Can any of you tell me what mr square is? Mass of the particle multiplied with square of distance from axis. What quantity is this?
Moment of inertia.
Moment of inertia of that particle. Okay. Therefore, the first particle's angular momentum is I1 into omega. First particle's moment of inertia about the axis multiplied with omega. Second particle's angular momentum will similarly be I2 omega and so on. Nth particle's angular momentum will be In omega. Now, the entire system rotates in the same sense. You can't have some part of the system rotating clockwise and some rotating anti-clockwise. In a rigid body, that is impossible. Okay. So all of them rotate in the same sense. Therefore, all their angular momentum, okay, or momenta will be in the same sense. Fine. And whatever is the sense of rotation, same is the sense of angular momentum. So whatever is the sense of omega, same is the sense of angular momentum L. Okay. So all these are in the same direction, so we can add them directly. Therefore, total angular momentum of the system will be right hand side. If you add all the terms, omega is common. There's no cross product involved. I mean, we didn't write in terms of cross product. I is a scalar. Moment of inertia is a scalar quantity. It's multiplied with angular velocity. So if you add all the terms on the right hand side, you get I1 plus I2 so on up to In multiplied with omega. And I1, I2 so on up to In is nothing but the total moment of inertia of the system multiplied with omega. Okay. Therefore, angular momentum of a system in rotation is moment of inertia of the system multiplied with omega. Now, moment of inertia changes from axis to axis. Okay, can change from axis to axis. Which axis should you take? About whichever axis you are calculating angular momentum, about the same axis you have to find out moment of inertia. So basically, this angular momentum and this moment of inertia must be taken about the same axis. And what axis is that? The axis of rotation. Okay. So here also we are using the fundamental formula mr cross v But when you apply that to all the particles and you add them up, it changes to this form I omega. And this is quite easy to remember actually. Formula for linear momentum is mass multiplied with velocity. Now, when it comes to rotation, the rotational analog of mass is moment of inertia, and the rotational analog of velocity is angular velocity. So L is equal to I omega. You can remember it like that. Okay. Fine. So for a system executing pure rotation, means rotation about a fixed axis, you can use L is equal to I omega. Moment of inertia about that axis multiplied with omega. Now, till now we talked about angular momentum of a point, and suddenly I started talking about angular momentum about an axis now. Okay, there is a slight variation, but the formula we have derived is fine. Now you can use it as it is. Okay, now how to adjust the equation from like what we the equation that we learned for a point, how to adjust that to an axis, that we'll discuss some other time, not now. For now, you can use this. Okay, so basically what is happening here is you see that the position vector r1 is perpendicular to the velocity vector v1. But the way I have drawn the system, the entire system is in the plane of your screen. Okay, but that same particle m1, assume it is out of your screen at a certain height above your screen. Then r1 vector, velocity vector, like it's difficult to explain. I'll make a 3D picture and show you in the next class. If you take their cross product, it will still be the same as this r1 cross v. Okay, even if the particle is out of your screen, then r1 vector tilts. Velocity vector will remain the same, but r1 vector, position vector will tilt. Okay, but if you take their cross product, it will still be this r1 multiplied with v. Okay, that I'll explain to you with a 3D diagram some other time. So remember, in rotation, for a system in pure rotation, angular momentum is I omega. For a system in pure translation, you can treat the system as a single particle placed at its center of mass and solve. Okay, let's solve one problem based on this quickly. Let's say a disk of mass 2 kg, radius 20 centimeters is spinning or rotating about its own axis with an angular velocity of 5 radians per second. Derive its angular momentum. Now you don't know how or which way it is spinning, so you can't tell the direction of angular momentum or the sense of angular momentum, but you can tell the magnitude. Derive the magnitude quickly. Okay, I got one answer as 0.2. We'll see. Yusuf, how are you trying to solve this? No response. Rishi? Okay. See, this is a system, like the disk is spinning about its own axis, so it's a system in pure rotation. What is the formula for angular momentum in pure rotation? I omega. I, you have to take about axis of rotation and multiply that with angular velocity omega. Fine. Now the disk is spinning about its own axis. Pawan, tell me, what is the formula for moment of inertia of a disk about its own axis?
Sir, mr square.
No. In a disk, all the mass is not at the distance r, no? Many particles are nearer. It won't be mr square. And see, I told you, moment of inertia, you have to remember, in fact, you have to derive and remember the moment of inertia about, the moment of inertia of regularly shaped systems, ring, disk, hollow sphere, solid sphere, okay? Rod about various axes. Anyone? What is the formula for moment of inertia of a disk about its own axis?
mr square by 2, sir.
mr square by 2. So r is 20 centimeters. You have to convert it to meters. R square by 2 multiplied with omega is 5. That's all. 5 into 0.2 is 1. 1 into 0.2 is 0.2 kg meter square per second. That is the angular momentum of this disk about its own axis. Next. Solve this carefully. A rod of mass, let's say 6 kg, and length assume is 2 meters, is spinning, okay, or is rotating about an axis which is not exactly passing through the center, not exactly at one end also. The axis is like this. Fine. And it's rotating with an angular velocity, let's say 10 radians per second. Okay. Derive its angular momentum about that axis. Think carefully and solve. Omega is already given to you. So basically, this is a question based on moment of inertia. If you know that, multiply them, you will get angular momentum easily. Think of how to derive moment of inertia of rod about that axis. Okay. The distance of the axis from one end is 0.5 meters. Can any of you tell me, okay, other than vanilla, why does that distance matter? It matters because moment of inertia of a system can vary from axis to axis. So you need to know where exactly this axis is. Okay, otherwise you can't express moment of inertia. Okay. Solve it quickly, 2 minutes. Okay, I got one answer as 35 kg meter square per second. Let's see. Now this is a system in pure rotation, and in pure rotation, angular momentum, okay. Fine, let's call length as L0 just to avoid confusion. Angular momentum is denoted by the symbol L, is I omega. So you need, omega is already known. So you need to calculate moment of inertia of the rod about this axis. Now the axis is perpendicular to the rod, but it's not passing through the center. It's not passing through one end. Because if it had passed through the center or one end, we already know the formula for moment of inertia. But about this axis, we don't. Fine. Then what can we do? One thing you can do is integration, or use some idea that we discussed for moment of inertia. Parallel axis theorem, perpendicular axis theorem, that compression idea, okay, or proportionality idea, something like that. Now, if you want to use parallel axis theorem, okay, you need to know the moment of inertia of a parallel axis passing through the center. Okay, the moment of inertia about a parallel axis passing through its center of mass. Rishi, can you tell me the formula for moment of inertia for rod about this other axis that I have drawn? Just the formula.
ml square by 4, sir.
No, for a rod, there is no, like, out of the formulas that we have discussed, whether it's perpendicular bisector or passing through one end, none of them is ml square by 4.
Oh, it's ml square by 12.
ml square by 12. Okay, we know ICM. Fine. And the other axis is parallel to this one. So we can use parallel axis theorem. But to use parallel axis theorem, we also need the distance between the two axes. Rishi, how much will this be?
0.5 meters, sir.
0.5 meters. Okay. So D is 0.5 meters. You know ICM, you know D, and you need to calculate I. Pawan, can you tell me the formula for parallel axis theorem? How do you make use of ICM to calculate I? Vanilla.
L square by 12 plus MD square.
ICM plus MD square. Okay. So I is equal to ICM plus MD square. ICM here is ML square by 12 plus M into the distance is 1/4 of the length. So I'll write it as L by 4 whole square. So it becomes ML square by 12 plus ML square by 16. 12 and 16 have LCM 48. And it will become 4 plus 16 is 3 times. So ml square. So the moment of inertia is 7 ml square by 48. And since we are calling the length as L0, I'll write it as L0. Okay. You can substitute it, get the moment of inertia, multiply with omega, you'll get angular momentum. Okay. So I'm repeating this. Moment of inertia is a very important concept. Anything you want to describe about a rotating system, you will need to know its moment of inertia. Okay. So keep practicing problems based on moment of inertia. Keep revising whatever we discussed about moment of inertia. Okay. Lecture video also is uploaded. Go through it if necessary. Fine. So if a system is executing pure translation, you treat it as a single particle placed at its center of mass and derive angular momentum. If a system is executing pure rotation, you use I omega. Okay, like linear momentum is mass into velocity. Angular momentum of rotating system will be moment of inertia into angular velocity. Okay, multiplied with angular velocity, right? Fine. So that is all you need to know about angular momentum in translation and rotation. There is something called combined translation and rotation also. In that case, how to find out angular momentum, all that we'll discuss later. So angular momentum is the rotational analog of linear momentum. Linear momentum tells you how difficult it is to stop a translating system from moving. Angular momentum tells you how difficult it is to stop a rotating system from moving. Okay. Now, one of you tell me, what is force, or what does force do to a system?
Or if the body is not rigid enough, it changes the shape of it.
Okay, what if it is rigid? We are discussing only rigid bodies as of now. What does force do to a rigid body, or try to do to a rigid body?
It tries to set the body in motion.
If it's at rest, it tries to set it in motion. If it's already moving,
Then it will try to keep it in motion.
you don't need something to keep it in motion. Object will stay in motion. Okay, it tries to change the state of motion. Okay, force tries to accelerate a system. No, it tries to change the state of motion of the system. Fine. So basically, force is a push or a pull, which tries to change the state of rest or motion of a system. Similarly, in rotation, we have a quantity called torque. Okay, denoted by the symbol tau. It's the rotational analog of force. What force does to translatory motion, torque does that to rotatory motion. Okay, force tries to change the state of translatory motion. Torque tries to change the state of rotatory motion or rotational motion. Okay, let's consider an example. Suppose there is a rod. Assume it is at rest. Okay, not translating, not rotating. And let's assume it is hinged or pivoted at one end. So somewhat like this. Let's say this is a rigid support. It is hinged at this end. Okay, means rod can rotate about that point, about that end. Fine. Initially, it's at rest. You can think of it as a door also. Okay, usually door has hinges at one edge. Fine. And if you look at the door from above, this is what it looks like. You'll only be able to see the edge of the door when you see it from above. Fine. Suppose you want to rotate this rod. let's say you want to rotate it anti-clockwise. Can one of you describe what you will do to it to rotate it? Or what do you do to a door if you want to open the door or close the door? What do
We
you
should
do?
pull it with a force.
You should apply a force. Correct. Okay. So, see, what you are trying to do is you're trying to change the rotational state. You want to make it rotate. But for rotation also, a force is needed. So, torque requires a force. To change the rotational state of a system also, you need a force. Fine. So, torque arises from a force itself. Torque is basically something which changes rotational state, but you know force is needed to change rotational state. So torque depends on force, or torque requires force. Okay, fine. So I'll give you a few cases here. Suppose we apply force this way, perpendicular to the rod or perpendicular to the door. One of you tell me, will the door rotate when you apply a force like this or not?
It will, sir.
It will. Okay, from everyday experience, we can tell it will. Suppose the force is applied here at the other edge of the door or other end of the door. Will the door rotate or not?
It will rotate.
It will. Okay, I want others also to answer. Suppose we apply force this way. Okay, Rishi, don't answer, someone else. Will the door rotate or not?
Yes, sir.
It will rotate. Correct. Suppose we apply force this way. Will the rod or door rotate or not?
No, sir.
Okay, Vanilla is saying no. Others, what do you think? Yusuf, what do you say? This yellow force, will it be able to rotate this rod or door or not? No. Okay. Howsoever strong the force may be, it won't be able to rotate the rod around this axis. Okay. It won't be able to rotate it clockwise. It won't be able to rotate it anti-clockwise also. Fine. What if we apply a force this way? Exactly at the hinge you apply a force. Will the door open?
No, sir.
It won't. It won't. Okay. So you can see that not every force produces a torque. Not every force has a rotational effect about a given axis. You have to visualize the axis carefully here. The axis is perpendicular to your screen. As I said, you are looking at the door from above. Fine. The hinges themselves are the axis of rotation. Okay. Hinge will be parallel to the door, no? So when you parallel to the edge of the door, okay, vertical edge of the door. When you look from above, it will look like a point. The hinge also looks like a point only when you see from above. Okay, so there's an axis there. And you can see that not all forces produce a torque about that axis. Not all these forces have a rotational effect. And some of these forces have more rotational effect than the other. For example, you consider the two orange forces. Let's say they are of the same strength. Tell me, is it easier to open a door by pushing it closer to the hinge or farther from the hinge? From everyday experience, you tell.
Far from the hinge.
Farther from the hinge, if you apply the force, it becomes easier to open it. Okay. So these two forces, F and F, that I have indicated, the forces are the same, exactly the same, but the rotational effect they produce is different. Fine. One of them produces less rotational effect, the other one produces more rotational effect. So force is not the only thing on which torque depends. It also matters how the force is being applied and where the force is being applied. Okay, the direction of force and the point of application of force, all of them matter for torque. Okay, now we know that, like, if you call these forces as F1 and F2, F2 produces a greater rotational effect than F1. Means F2 produces more torque than F1. Now, what's the only difference between F2 and F1? The distance of the point of application of force from the axis. Okay. One is at a shorter distance. You can call this as R1. The other is being applied at a greater distance. You can call it R2. And because R2 is more than R1, we see that it produces a greater rotational effect or greater amount of torque. So you can say that the magnitude of torque is proportional to R, where what exactly is R? Distance of the point of application of the force, exact point where the force is acting from the axis. That is what is R. Okay. So greater the distance, greater the torque produced. That's one of the factors on which it depends. And obviously, stronger the force you apply, greater will be the torque produced. So torque is proportional to magnitude of force as well. Okay, more force can produce more torque if it is applied in the right manner. Okay. Now you look at that yellow one. That yellow force is being applied at the end point of the rod. Okay, it has significant R value. It may have a significant magnitude of force also, but it's not able to produce any torque. Why? It's not the complete force that matters. To rotate something about an axis, it's the component of force perpendicular to the position vector that matters. For the yellow vector, there's no force perpendicular to position vector R. For the orange vectors, okay, the entire force is perpendicular to the position vectors. F1 is perpendicular to R1 vector, F2 is perpendicular to R2 vector. So they produce torque. Now you consider the green one. Let's call this as F3. Okay. Now F3 can be resolved into two components. You can take one component of F3 perpendicular to the position vector, and you can take one component of F3 parallel to the position vector. Pawan, tell me, which of these components, perpendicular component or parallel component, has or can rotate this door about the given axis? Which component of F3 can produce a rotational effect? No response. Okay, Rishi, tell me which component of force F3 can produce a rotational effect?
Sir, perpendicular.
Perpendicular component, correct. So torque depends on the distance where the force is being applied from the axis, and it also depends on the component of force perpendicular to the position vector. So you can say torque is proportional to R multiplied with F perpendicular. Now R is a vector, force is a vector. What should you do to two vectors to get one vector multiplied with the perpendicular component of the other? You have to take cross product. Therefore, torque produced by a force, okay, can be expressed as R cross F. Okay. Now there's another possibility also, F cross R. In both cases, the magnitude is R multiplied with F perpendicular, right? Now, which cross product to take? Let's see. One of you tell me, in which sense will the force F1 rotate this rod? Clockwise, anti-clockwise? In which sense will?
Anti-clockwise, sir.
Anti-clockwise. Okay. So the torque, that's nothing but the rotational effect produced by F1, should be anti-clockwise. Now what we are trying to find out is whether torque should be written as R cross F or F cross R. Okay. Now What's the difference between R cross F and F cross R? The sense of rotation will be different. The direction will be opposite. Okay. So which direction exactly it is, we want to find out. Okay. Now here the torque produced by F1 has to be anti-clockwise. Okay, it is anti-clockwise, we know that. Now we have to decide which of these cross products is anti-clockwise. Whichever is anti-clockwise, that becomes the formula. So one of you tell me, what is the sense of R cross F? R1 cross F1. Is it clockwise or anti-clockwise? Or direction of cross product is into the plane or out of the plane, you tell.
Into the plane.
Sir, R
Okay, Vanilla is saying into the plane. Next.
outside the plane.
Okay,
F
Rishi,
cross
why do
R.
you say it is out? Who asked you to take F cross R? I am asking you the direction of R cross F.
Oh,
Is it clockwise or anti-clockwise? Is it into the plane or out of the plane?
into the plane.
Into the plane. We'll see. Aishwarya, what do you say? Okay, Vanilla, you tell me, how did you decide that it is into the plane?
By right hand thumb.
Right hand thumb rule. How do you apply that? First, along which vector should you move?
R bar.
You want R cross F, so move along the first vector R. Then which way should you turn? You have to turn towards the direction shown by F. Okay, F is showing upward direction here. So R cross F is like this. Just because we drew the vector on the lower side doesn't mean you turn this way. Okay, the direction shown by F is upward. So you have to turn that way. Now curl your right hand fingers this way. It's an anti-clockwise sense. Okay. So R cross F is anti-clockwise. F cross R will be clockwise. Now we know that the torque produced by F1 is anti-clockwise. Okay, it rotates this rod anti-clockwise. So should you use R cross F or F cross R to find out torque? You should use R cross F. Okay, therefore the formula for torque produced by a force, torque means rotational effect. So rotational effect produced by a force about a certain point is R cross F. Again, I said about a certain point. The discussion was about an axis. Okay, but I use the word point now. Okay, that is because this position vector R, see, vector can be drawn from one point to one point. You can't draw a vector from a line to a point. Okay, you can draw it from a point to a point. So this position vector R is, I can say, is the position vector of, remember this all of you, okay, point of application of the force, point of application of the force, okay, with respect to the point about which you want to calculate the torque. So about which the torque is to be calculated. Okay, what if it's an axis now? Okay, let us understand. We'll have to spend some time on this. Listen carefully, all of you. Consider an axis. Axis is nothing but a line. Consider some point here where a force is acting. Okay, and how shall we assume the force to be acting? Let's assume it is acting into the plane of your screen. So cross inside a circle indicates inwards. So assume the force is acting inwards. Now from different points on this line, you can draw different position vectors to the point of application of the force. From this point, this is the position vector. Okay, let's call this point as A. With respect to A, this is the position vector. Okay, So this is R with respect to A. With respect to some point here, this might be the position vector. So let's say for B, for the point B on the axis, this is the position vector. Some other point will have some other position vector and so on. Infinite different position vectors can be drawn. Now see, if you want to talk about the point A, then it is RA, position vector from A, cross the force F. Okay. If you want to talk about the point B, then it is position vector drawn from B, cross F, and so on. So about different points, you can get different magnitudes of torque. That's fine. Listen, force is acting into the plane of your screen. You look at the point A. Okay, let's just consider A and the force. Let's remove everything else. Let's only consider A and the force. Situation is like this. So force is acting into your screen. That's the point A. So basically what this force tends to do is, it tends to rotate whatever system is there. It tends to rotate that system in a circle like this. Around that point, that is how it tends to make it rotate. Hope this is clear to all of you. So RA cross F tends to make the system rotate this way. Okay. Now, we had an axis here on which A was one of the points. Now, if this is an axis, what the system can do is it can only rotate around the axis like this. Okay, it can't tilt and rotate. If it is tilting and rotating, then this becomes the axis. Fine, but we are looking for torque about a particular axis, right? So you have to find out how much rotational effect that force has about this axis. Now, if you want torque about this axis, what you need to do is you will have to take this position vector. Fine. If you take this position vector and the force is acting into your screen. Position vector is along the x-axis. So force is acting along z-axis perpendicular to your screen. Position vector is along x-axis. Then the rotational effect will be around the y-axis. Fine. That is one thing you can do. You have to take the position vector to the point of application of the force, which is perpendicular to this axis. Now, how do we do that? Axis is a line. How can we find out that position vector? You can't. Okay. I mean, as such, directly you cannot. But there is a relation between RA and R. Okay. It's like R is the component of RA. Which component? X component. Is that clear or not? Are you all able to visualize that? That R is the X component of RA. Yes or no?
Yes.
It is. It is. Okay. Now, if you take RA cross F, okay, you imagine moving along RA and then turning into the plane of your screen, okay, going into your screen, and then curl your right hand fingers. RA cross F will be this way. This is the actual torque produced by the force about the point A. Okay, this is RA cross F's direction. We don't want RA cross F. We don't want torque about the point. We want torque about the axis now. That is what we are trying to express. Torque about the axis is R cross F. Okay. And R cross F's direction will be this way. This is R cross F. Okay. Now R is the X component of RA. Suppose this angle is alpha. If this angle is alpha, automatically this angle also will be alpha. Okay. The angle here being 90 degrees. If the angle made by RA with horizontal is alpha, then the angle made by RA cross F with vertical will also be alpha itself. Okay. Therefore, R can be written as RA cos alpha. So basically what we are looking for, I mean the torque that we are looking for, torque about the axis, is R cross F, which is R multiplied with F perpendicular. And that becomes RA cos alpha multiplied with F perpendicular. The force is anyway perpendicular, we have taken that. And this original torque about the point A, not about the axis, about the point, it is RA cross F. Okay, that is RA into F perpendicular, the component of force perpendicular to your screen. Now, what's the relation between torque about the point and torque about the axis? Only that cos alpha is the difference. Torque about point is RA multiplied with F perpendicular. Torque about axis is RA F perpendicular cos alpha. Therefore, you can say the torque about the axis is torque about a point multiplied with cos alpha. That is nothing but component of torque about a point along the direction of the axis. See, this is actually some in-depth discussion. Okay. Basically, an axis is a collection of infinite points. Now, if you want to find out torque, you have only one formula, R cross F. R should be taken from point to point. Okay. So what I'm indirectly saying, or what is the summary of all this, is that you take any point on the axis, do cross product with the force. Okay. So you get RA cross F. Then take its component along the axis. That will be the torque about that axis. Okay. So for torque about axis also, the formula we use is torque about a point only. And then we take its component. So you can do RA cross F and then take its component. Otherwise, there's one more thing that you can do. If you can visualize R vector, then you can do R cross F directly. How to visualize R vector? You have to see from above. If you look from above, the axis will appear like a point to you. Okay. Like fine, like this. Yeah. For the rod or door, the hinge is the axis, but when you see from above, it looks like a point to us. Now, this force F1 could have been acting at any point of the door. I mean, at any height of the door. We know at what distance from the hinge it is acting, but at what height it is acting, we don't know. And it doesn't matter. Okay. All you need to take is this perpendicular distance. Okay. So when you look from, what do you say? When you look from an angle from which axis appears like a point, then that perpendicular distance will be very easy to visualize. Then you can take that vector cross F directly. Okay. Anyway, see, some of you might have understood this completely. Some of you might not have understood, but as we solve problems, you will get comfortable with all this. So effectively what I want to say is torque about an axis is torque about any point on that axis and its component along the axis. That's all. Okay. So you can take any random point on the axis and find out torque, take its component. Otherwise, you visualize this perpendicular distance or this perpendicular position vector you visualize, then take cross product, you will get the torque about the axis directly. Okay. So basically the formula for torque is R cross F, where R is the position vector of the point of application of the force with respect to the point about which you want the torque. Okay. And as you know, A cross B, if you know vectors, you can take the cross product directly. Otherwise, you can find out magnitude first and then assign a direction. How do you find out magnitude? A multiplied with B perpendicular or B multiplied with A perpendicular. Okay. So the magnitude of torque can be found out this way. Magnitude of R cross F, no? So you can take R multiplied with F perpendicular. You can also take F multiplied with R perpendicular. Mathematically, they are the same. Okay. So one of these ways you can calculate the torque. Fine. Let's solve some problems based on this. Suppose there's a random system and there's an axis here. Now, on one point of that system, there is a force acting like this. How much force shall we take? Maybe 10 Newton. Okay. And how far is that point from the axis? This position vector, let's say this distance is 5 meters and this angle, let it be 120 degrees. Okay. So first of all, tell me, a 10 Newton force acting like this, will it be able to rotate the system around this axis? Means will it be able to rotate it clockwise or anti-clockwise or not? Will it not produce any rotation? Rishi, what do you think? Will this 10 Newton force acting the way it is acting be able to rotate this object around that axis or not?
Sir, I think it might, but like not very much.
Will it or not? How much I'm not asking. Okay, just yes or no. Yusuf, what do you think? Aishwarya, will this 10 Newton force be able to rotate the system about the given axis or not?
Yes.
It will. In which sense do you think it will rotate? Clockwise, anti-clockwise?
Clockwise.
Clockwise. Vanilla, what do you say?
So it will rotate clockwise.
Okay, rotates clockwise. That is correct. It will be able to rotate clockwise. Fine. So it can produce a torque. Calculate the torque. Do this quickly, all of you. I'll give you all 2 minutes. Solve carefully and I want answers from all of you. Okay, within 2 minutes, do whatever calculation you can do. Okay, apply the formula and whatever answer you get, send it to me. I got one answer as 25. 25 is not correct. Rishi, the force is not perpendicular to the r vector. No, you have to take component of force perpendicular to r vector. Pawan, your answer is correct. Okay, so there are two things that you can do. The magnitude of torque is r multiplied with f perpendicular or f multiplied with r perpendicular. Let's try this first. So we are going to take r as it is, 5 meters. That is r. Now the 10 Newton force is not perpendicular to that 5 meter vector. So you have to take the component of 10 Newtons perpendicular to that vector like this. Total angle is 120. We want perpendicular component, means this side angle is 90. That remaining angle will be 30 degrees. What's the component of 10 in this direction? 10 cos 30. 10 root 3 by 2, that is 5 root 3. So r is 5 meters. Perpendicular force is 5 root 3 newtons. So the torque becomes 25 root 3 Newton meters. Okay, that is if you take r multiplied with f perpendicular. Now you can do one more thing also, f multiplied with r perpendicular. Let's see how to do that. F is the force, that's okay. R perpendicular should be from where to where? Now, just like how we had in angular momentum. In angular momentum, r perpendicular was the distance from axis to the line of action of velocity. Because there we needed r cross v. So we took distance to the line of action of velocity. Here for torque, we need r cross f. So we'll take perpendicular distance from the axis to line of action of the force. So you need to visualize the line of action of force and take the perpendicular distance between axis and that line. This distance. Okay, we'll have to apply some trigonometry for this. The total length is 5 meters. The angle made with velocity on that side is 120. Then this angle will be 60 degrees. If this is 60, okay, 180 minus 120, 60, then this becomes 30. If this is 30, then the perpendicular distance here, R perpendicular, will be 5 cos 30, 5 root 3 by 2. So if you want to use F multiplied with R perpendicular, F is 10 newtons, R perpendicular is 5 root 3 by 2. 10 into 5 root 3 by 2, 50 root 3 by 2 is still 25 root 3 Newton meter itself. Okay, but in this particular case, multiplying R with F perpendicular is easier than F with R perpendicular. But I showed you both ways just to make you understand from where to where R perpendicular is to be taken. So you can calculate torque in one of these methods. Is this clear to all of you? Like 3 of you gave the correct answer. Others, Rishi, Yusuf, did you understand? The complete
Yes,
force
sir.
does not produce a torque. Only the component of force perpendicular to position vector produces a torque. That is the idea. Okay, fine. We'll stop it here for now. But I will take one class on Sunday. Okay, and we'll be solving problems on angular momentum and torque exclusively. You have to be very comfortable with these quantities, not just because they are in this chapter. You are going to come across angular momentum and torque in almost all chapters from now onwards. And you should be very comfortable calculating these quantities. So I want to take one class based on calculation of angular momentum and torque. Okay, we'll have that on Sunday. Okay, thank you all. We'll continue on Sunday.